Today, Shivam and I will be presenting our exploration into the effects of climate change on Colorado groundwater and offer some results and conclusions from our findings. So on screen are 4 charts from the IPCC's 5th report, which really hits on the main drivers of our current climate state. Land and ocean temperature anomalies have been increasing, greenhouse gas concentrations have been increasing, CO2 emissions from fossil fuels have exploded since the 1950s, and while sea level had already been rising in recorded history, the rate has been growing, and it's directly linked to human-generated greenhouse gas emissions. The good news is any incremental offset to greenhouse gases will drastically decrease the long-run economic impact, therefore placing importance on the use of prediction and to analyze and calculate these risks. So we wanted to do something regarding climate change, but we didn't know exactly where to start. The original concept was to reproduce global climate change trends and evaluate against the IPCC's representative concentration pathways or RCP scenarios. These represent varying levels of carbon emissions and their probable impacts to climate and humanity. Upon further research, we found 2 studies, one done in Germany and the other done in Iran, that utilized machine learning techniques to analyze future groundwater levels using these RCP scenarios. With that framework set, with the existing academic research in hand, we decided to pursue a similar study with Colorado groundwater levels. So here you'll see 3 sites we chose to pull groundwater data via API from the United States Geological Survey. While there were hundreds of water reading sites to choose from, these 3 happen to be USGS official sites and also conveniently had precipitation and temperature readings to pull as well. One thing to note, we ended up dropping Kit Carson in the final model run. It's pretty apparent here as it was lacking a consistent start date. Essentially, the data wasn't complete enough for us to proceed. Here's a closer look at our 2 selected sites, scaled a little bit better to depict some seasonality. For the Muddy Creek site, we observe an increasing trend, while the Puebla site looks quite a bit more seasonal. Upon further investigation, we found that the Muddy Creek location is a well monitoring aquifer readings, while the Puebla site is specifically a drought well, which might help explain that fluctuation, like perhaps water is drawn in drier seasons. Next up, we have average temperature for our 2 selected sites. Temperature is a great proxy for evapotranspiration, or the rate that groundwater evaporates. As you would expect, very cyclical and tied to our weather seasons in Colorado. Next up is precipitation data from both sites. This will serve as a proxy for groundwater replenishment. Now that we have precipitation, temperature, and groundwater data, we just needed modeled RCP data to provide data and validation against our results. Originally, we tried to pull RCP data from the Coupled Model Intercomparison Project datasets, or CMIP as it's typically referred to. As it turns out, global 1,000 kilometer resolution climate data to 2100 is a bit difficult to pull and even more difficult to work with. What we ended up finding is a project called CORDEX under the World Climate Research Program. The CORDEX stands for Coordinated Regional Climate Downscaling Experiment, where several other modeling groups participate in downscaling CMIP data to a more regional outlook at finer resolutions. Here we have 2 scenarios, RCP 4.5 on the left and RCP 8.5 on the right, at a 50-kilometer scale and filtered down even further to the Colorado region. To touch on RCP a little bit more, RCP 4.5 generally represents a base case scenario, while the RCP 8.5 generally represents a worst case scenario. The number 4.5 and 8.5 corresponds to the expected change in radiative forcing, or in other words, change in energy flux in the atmosphere caused by human influence factors from the year 1750 to 2100. In blue, we have historical data we pulled, and in orange would be RCP modeled projections into 2100. So with that, I'll pass it over to Shivam to talk through modeling techniques and results.
Starting with the data collection phase, we collected our climate data from NOAA website and the groundwater level data from USGS website, both via API, which were then processed and cleaned to have a final data set for both climate and groundwater level. Now, this clean data set was passed inside feature engineering pipeline, where we generated engineered feature for the time series, as the past data is heavily used or enforced in present predictions in time series. So the engineered feature that we generated are like 7 days rolling mean, past 14 days rolling mean, 1 day lag data for the current data. We create a model structure. We train those model structure on the train and validation data and analyze the loss curve for train versus validation, and then based on the loss curve we select a parameter, and this entire process is an iterative process until we finalize the final parameter. We iterate this process over and over to ensure that we are selecting model which has minimal loss in terms of our loss parameters and the functions. Now, once the model is trained, we save this model for further use, and this model is used to generate projections on the data that is for the climate data greater than 2024. And that data is something that we fetch using Cordex project. We fetch data for RCP climate projections for 2024 year and later until 2100, and use that data along with our modeling data to create projections for groundwater level. And now coming towards the model results. So as we have two sites, Muddy Creek and Pueblo. Talking about Muddy Creek, this graph represents the predicted versus actual for H1 2023. Now, just touch base on the training data. We trained on the data from 2015 till 2022, and that was used as 80% for training and 20% for validation for parameter selections. And the 2023 data was used for testing to see how good our model is performing. Now, for Muddy Creek, if we look at H1 or before of June 2023, this is the curve that represents the predicted versus the actual, along with the 95% confidence interval. And the error metrics we have is the mean absolute error, which is just 1.21, with the unit being same as groundwater level, and the percentage error is around 9.5. But if we observe the same results for H2 of 2023, the results look better. So the mean absolute error goes down to 0.31 and the percentage error goes down to 2.7%. And similarly, if we look at results or on Pueblo County data for H1 2023, this is the graph we have for predicted versus actual groundwater level. And the error metric, that is the mean absolute error, is 0.57 versus the percentage error is just 2.6%. And for the H2 2023 for Pueblo County, the mean error drops to 0.31 and the percentage error drops to 2.6. Now, coming towards the analysis of model. So there were multiple engineered feature that we created out of the temperature and precipitation we had to pass it towards our model. Now, to understand which feature is impacting how much predictions in the model, we have the sharp values. This plot basically tells us that for each feature, what is the contribution being made towards the end result prediction. And if we look at Muddy Creek model, we see that precipitation is the major contributor towards the prediction, while for Pueblo model, the temperature is the major factor influencing the predictions. Now, moving towards the projections in which we are using the train model to project the groundwater level for 2024 till 2100. This is how the data looks like for the projections. And we see that the red line represents the average over the entire time frame of what the groundwater level would be. We observe that there is a major dip in groundwater level somewhere around 2065 to 2070. Similarly, for Pueblo based model, this is the groundwater level projections from 2024 till 2100, considering the RCP 8.5 scenario. And the red line again represents the average of the groundwater level over the entire time frame. Coming towards the limitation of this entire project and the model specifically, we considered only temperature and precipitation as the factors passed inside the model, and our results are totally based on that. There are still other factors that we want to incorporate inside our model, like the gases effect relevant to the temperature and pressure and the climate. So that is something that if we incorporate, we believe that the results would change. Also, the model training was done on 7 year worth of data from 2015 to 2022, but the results are being projected from 2024 till 2100. That's like over 7 decades of projections, and that is causing some inherent bias because of the difference between the amount of training data and the projection data. The last limitation is the bias with respect to the well region and the consumption rate for each well. And these are the references for our project. Thank you.